So, for the rest of this unit, we're going to explore uh, the derivative of e to the x. We're going to look at the derivative of ln, the derivatives of logs and exponents in general, some logarithmic differentiation, and growth and decay. In this lesson, this is 4.3, we are going to explore the derivative of e to the x. So, the exponential functions occur very frequently in various areas of study: science, business, banking. So I want you to consider the following example. Imagine you deposit $1 into a magical bank account that compounds interest infinitely fast. How much money will you have after 1 year? Remember, with simple interest, you can earn a fixed amount, but with compound interest, the more frequently it's compounded, the more money you make, the greater the final amount. So, the equation for compound interest is total amount at the end is equal to 1 plus 1 over n, all raised to the power of n. N is just the number of times it's compounding, and A is the total amount at the end. So if we were to think about this a little bit and we were to set up a chart like this with our equation over here, 1 plus 1 over n to the power of n. If our interest was compounded once a year, so only one time a year, and we plugged that into our equation, we'd have 1 plus 1 over n, or 1 over 1, raised to the power of 1. That would give us 1 plus 1. That equals 2. So we would end up compounding interest twice. If we compound it monthly, that's 12 times per year. This function ends up approaching 2.6. Now, if it's compounded daily, so 365 times per year, we get a value approaching 2.714. And if we make this a really, really big number, so as n gets closer and closer to infinity, so if the interest gets compounded infinitely often, it will actually approach a very special number. So if we were to have this interest compounded a million times a year, we see that our value approaches 2.718. And actually, it will, as it gets bigger and bigger and bigger, approach 2.7182828. And this is the number E, or Euler's number. And it's a very well-known irrational number in math, very similar to pi. It's non-terminating, non-repeating number. And if you would like a little bit more information about Euler's number specifically and how that works, how we've come up with the value of E, you can go ahead. I did post a video, not my own video, but a video for you to watch on the VLE that will help explain that. So if we take a look at what this looks like graphically, so if this is my number, if along the X I have the number of times it's compounding, I have my dollar amount here, we can see that as the number of times it compounds gets larger and larger, and as n approaches infinity, the dollar value also approaches infinity. And where have we seen this before? Well, you've seen it before in the function f at x is equal to e to the power of x, maybe, or y is equal to e to the power of x. This is referred to as the natural exponential function, and the word natural refers to this actual value of e. So in functions, you would have looked at logarithmic functions. So you would have looked at things like log 42 plus log 432. And you probably would have used some rules that say that log a with two values like that is equal to the two of them separated but added together. Sorry, that's a little bit messy. I'm running out of space. You may also have seen the natural log, where we have log of e at some value, say 5. So this is our base value, and this is a base of e. Remember, e is just a number. So log base e, 5, is just a logarithmic function with base e. We're going to take some time today to take a look at what the derivative of that looks like by taking it back to first principles. Okay, so as promised, we are going to go back to first principles and to our definition of the derivative, and we're going to use limits and the definition of derivative to determine what the derivative of y equals b raised to the power of x, or some function that now is not something squared, but now our exponent is our x value. So we've seen this before. Remember, when I'm taking the derivative, when I'm taking my derivative, the derivative of any function is equal to the limit as h approaches 0 of f at x plus h minus f at x all over h. So now if we were to take this and sub it in, sub x plus h and x in for the x that's in our function, we end up with the limit as h approaches 0 of b raised to the power of x plus h minus b to the power of x all over h. This looks a little different from what we've had. So to work with an exponential function like this, we need to use our exponent rules kind of in reverse from grade 9. So we are going to split this up. So instead of putting it together like we would have, we're actually going to split it up. And we end up with the limit as h approaches 0 of b to the power of x times b to the power of h. So I've just split it up. We know that if two exponents are being multiplied together, or if you have two bases with an exponent and they're being multiplied together, we can add them. So we're just, like I say, doing that in reverse, minus b to the x all over h. Now, instead of adding the exponents, I said that already, we are going to separate them out. The reason that we do this is so that we can take a common factor. So if we pull out a common factor out of here, we end up with the limit as x approaches 0 of b to the x times bh minus 1 all over h. Now, normally we would think of x as the variable, but here it's h that's approaching 0 and h that's changing. So h is the variable and x in this case is the constant, so we can move it to the front. So since it's a constant and it can be moved to the front, we also can move it in front of the derivative. So we're going to move that b to the power of x right out in front of the derivative. So now we have b to the power of x as h approaches 0 is equal to b to the power of h minus 1 all over h. So our derivative is b to the power of x times the limit as h approaches 0 of b to the power of h minus 1 all over h. That means that the value of b we actually put in here changes our derivative. If it was 2, that would be different than if it was 3 to the power of x or 4 to the power of x. So the question is, what gives us the easiest derivative to work with? What base would we like? What would be the best? The simplest value we could get would be if the derivative was 0, but that would only occur when b equals 1. And I've put that here. I did it on Desmos, and I thought we could take a look at it. So as h approaches 0, our derivative is 0, but it's really a trivial case because y equals 1 to the power of x is simply a horizontal line like you can see here, and it's the same as saying y equals 1. The next easiest we could do would be 1. So now what happens if we have, what happens as h approaches 0 of b to the power of h minus 1 over n, if it equals 1? Well, take a look at what's happening here. As it equals 1, you can see that the base is going to be about 2.7. This occurs when the base is about 2.7. So if we take a look over here, we can see that our b value is 2.7, and that happens y will equal 1 when the base is about 2.7. If you watched the other video I posted for this lesson, you would know that we're not really looking at 2.7. We're looking at that irrational constant similar to pi, except that the value is about 2.7, and that number we're going to call e. So, as the title of this lesson suggests, we really want to take the derivative of e to the power of x. So, the goal today is to find the derivative when y equals e to the f at x, where the derivative of e to the x is actually just e to the x. So, from first principles, that limit disappears because it equals 1. And all that's left is the derivative e to the x equals e to the x. So this means that for any value of x, the slope of the tangent to the curve y equals e to the power of x is equal to the y coordinate. So if the y coordinate is 2, the slope is 2. If the y coordinate is 3, the slope is 3. So let's see what happens if we add a little extra in there, not just e to the x. So instead of e to the x, it will be y equals e to the f at x. So let's look at this one. So we have y equals e raised to 3x. So think about the chain rule and Leibniz notation as we look at this derivative. We're going to start by making the substitution, and we're going to let u equal 3x. So remember, we're looking at having these be two different things. We have our number e, and we're going to have 3x equal u, and that's going to equal 3 to the x. So now if we rewrite this, we have y equals e to the power of u. But there's no x's, and we want dy over dx. Remember, that's that Leibniz notation, dy over dx. So we use our chain rule in Leibniz notation. And remember, that just says that it's the derivative of the first times the derivative of the second. Or the outside times the inside, or the upper times the lower. We're just going to use our chain rule. So the derivative of y with respect to u, and the derivative of u with respect to y. So like I say, dy over dx, that's the derivative that we want. Dy du, so this is the one we want. And dy du is the derivative of y written in terms of u. We already know that the derivative of e to the x is just e to the x. We saw that on the second slide. So the derivative of e to the u must also be e to the u. So du over dx is the derivative of u written in terms of x, and that derivative is simple. It's just 3. So let's take a look at what our derivative is. So we would have dy over dx is equal to. So our derivative of dy to du is just going to be what we already have, e to the u. And my derivative of the upper part, 3x, is just 3. So derivative of this part times the derivative of the top part. Now we're going to put 3x back in there. So if we put our 3x back in there, we have dy over dx is equal to e. We're going to replace this with 3 to the x, and then our original 3 stays there. The simple way to think of it is the derivative of e raised to the power of f at x is the same thing times the derivative of the exponent. So we would have, we can think of e at e raised to the power of f at x times the derivative of f at x multiplied by the derivative of the exponent. And that's it. So e raised to the power of anything, the derivative of that is just the same thing, e raised to whatever the power is. And we multiply that by the derivative of whatever the power is. And it is really that simple. We're going to take a look at another example, another couple of examples here in a second. Okay, so let's look at some examples. So let's determine the derivative first off of y equals e to the x squared. So the derivative is the same. Remember, the derivative of this is the same thing multiplied by the derivative of the exponent. Okay, so here we go. So that would mean that y prime, or our first derivative, is equal to, so this whole thing is, we rewrite it, so e to the power of x squared times the derivative of the power. Remember the power rule. We bring the 2 down. So the derivative of that is 2x. We can rewrite this by moving the 2x in front. So we end up with 2x times e raised to the power of x squared. That's it. That's all we have to do for that. So the derivative of e raised to the power of anything is just that. And then you take the derivative of whatever it's raised to. Now, this next case is a little bit different because we're multiplying two functions that have an x. So now we have to use the product rule. So remember, just as a reminder, the product rule says that we take the derivative of the first times the second plus the derivative of the second times the first function. And it doesn't matter which order you put these ones in because we're adding, so order doesn't matter. So let's take a look at this. So we have the e to the x stays the same. So we're going to flip it this time, and we're going to go do derivative of the second times the first plus derivative of the first times the second. It doesn't matter. So our e to the x stays the same as our derivative. So that's our derivative of our second times our first plus the derivative of the first. So the derivative of x squared is 2x. And then times our original, which is e to the x. So it's the second one multiplied by the derivative of the first. The nice thing about exponential functions is that since the original shows up in the derivative, we will always have a common factor. And our common factor here is actually, so our common factor, here is x e to the x. So I can pull that out from there. So this becomes x e to the x all times x plus 2. Notice that this is nice for calculating our critical points when we have to do our first derivative test and determine the critical points. This makes it very easy to do. So now this one, our final one here on this page, is a little different because we don't have x in both terms. Remember, e to the power of 2 is just a number, the same as pi. Pi is just a number. E to the power of 2 is just a number. It's a constant. It's no different than having 3 to the power of 2 times x. So if we take the derivative of this, e to the power of 2, so we end up with the derivative of just e to the power of 2. The derivative of a constant times x is just the constant. That's it. That's all she wrote for that one. So for this one, this would be the same, just as a bit more explanation. This would be the same as saying I have 2x and I want to know what the derivative of that is. Well, the derivative of 2x is just 2. So if we're taking e to the power of 2 as just being a constant, the derivative will just be, so now we have e to the power of 2x. And so the derivative of that is just the constant, which in this case is e to the power of 2. Let's finish with one application example. So we want to determine the absolute maximum value of f at x that equals x times e to the negative x. The maximum value, remember, means that we're looking for when the derivative is equal to 0. So to do this, we have x times e to the negative x. This will be the product rule, because I have two functions multiplied together. So we're going to take the derivative. That's our first step. We're going to take the derivative. So our first derivative, we have derivative, the first times the derivative of the second. So the first is just x. The derivative of the second, remember, we have to use the power rule a little bit here because it's raised to a negative power. So the derivative of the second will be negative. We're bringing that negative down. but then it's just e to the negative x, right? Because e raised to the power of anything is just going to be e, or the derivative of an exponent is just the same thing. Now we have plus the derivative of the first times the second. So the derivative of the first, just x, is 1. We don't need to rewrite it. And the times the second is e to the negative x. So we have e to the negative x. So our first derivative is x times negative e raised to the negative x plus e raised to the negative x. So now let's set this to 0. One thing we're going to do first, we're going to pull out that common factor. Remember I said when we've got these exponents, they typically lend themselves to having a common factor. So we actually are going to pull out the common factor of e to the x. And when we do that and set it equal to 0, we end up with e to the x on the outside, negative x plus 1. So we can see then that x is going to be equal to 1. So now we need to figure out what the y value is. So we're going to sub x equals 1 back into our original question or original equation of x e to the negative x. And when we do that, we get our critical point of 1 over e. 1 over e. So now we need to prove that this is an absolute maximum value and not just a local maximum. And to do that, we're going to do the second derivative test. So we're going to go ahead and we're just going to take the second derivative. So our second derivative will be x e to the negative x. Because I bring the negative 1 down, so the negative 1 comes down, that comes back to being positive, plus negative e to the negative x times negative e to the negative x. Okay, so I've used the product rule again for here. Then I just added, not times there, I made a mistake. It's not times there, we're just adding that on the end. Minus e to the negative x. So then we've added this on the end because the derivative of e to the negative x, which is negative e to the negative x. Okay, so if we simplify, we have an e to the negative x in every part, so we can take that out. And when we take that out, so there's my e to the negative x because we have it here, we have it here, we have it here. I can pull it out of everything, and that leaves us with e to the negative x times x minus 2. If we put 1 into this equation for our second derivative test, we find that the second derivative at 1 is going to be less than 0 because this 1 minus 2 is going to be a negative 1. That's going to give us a negative answer. Therefore, this is concave down. So this is concave down. And therefore, it will be a local max. Since this is a continuous function and there's only one turning point, then it must also be the absolute maximum. And by continuous, I mean that there's no asymptotes or breaks in the curve, and it reaches a high point at 1 over e, and then goes down again. If you're ever not sure, check with Desmos. So to finish this out, we can write the final statement that therefore, the absolute max, so therefore the absolute max is at 1 over e. Okay, so here are some questions to try on exponential functions. This for sure is a topic that you will see in any university calculus course. There will be an exit ticket posted at some point today also for this lesson as well.